What if the heart isn't the full story of circulation? What if blood is not simply being pushed through pipes, but guided, organized, and even electrically driven by the structure of water itself? For generations, we've imagined the vascular system as mechanical. The heart pumps, pressure pushes, blood moves, but there's a problem with that model. At the microscopic level, inside the smallest capillaries, blood flow behaves in ways that pressure alone struggles to explain. Something else appears to be happening, because inside your blood vessels, there exists a highly organized interface where water becomes structured, electrical charges separate, and flow begins to behave less like hydraulics and more like an energy system. And at the center of that system may be carbon dioxide, not as waste, not as a toxic gas, but one of the key regulators of vascular charge, proton gradients, and biological coherence itself. The inner surface of every blood vessel is coated with an incredibly delicate structure known as the glycocalyx, made of sugars, proteins, sulfated molecules. It forms a true interface between blood and tissues. And what makes it important is not just its structure, it's its charge. So the glycocalyx carries a strong negative electrical charge. And wherever water encounters a charged surface like this, it changes state. Instead of behaving like ordinary liquid, it organizes itself into highly ordered layers, structured water, more coherent, more gel-like, more electrically organized. Solutes are pushed away, charges separate, friction falls. So instead of blood scraping against the blood vessel wall, the glycocalyx creates a lubricated electrical corridor, you could say, where blood flow occurs with less resistance. Red blood cells are part of this architecture too. Their membranes carry negative charge, keeping cells separated, preventing aggregation, allowing smooth, coherent movement. This isn't mechanical spacing, it's electrostatic organization. And this is where carbon dioxide becomes especially important. When CO2 levels fall, oxidative stress rises, the glycocalyx begins degrading, and the negative charge on red blood cells weakens. Cells begin clumping, flow becomes turbulent, the vascular system loses coherence, circulation is organized at the interface, and carbon dioxide helps preserve the conditions that allow organization to exist. So if the glycocalyx creates the interface and structured water creates the conditions for organized flow, where does electrical energy come from? Because a battery cannot exist without a charge separation. And charge separation requires particles carrying charge. This is where we arrive at one of the most overlooked aspects of physiology, protons. Protons carry positive electrical charge, and wherever they accumulate or are displaced, electrical gradients form. The main system that powers your mitochondria may also operate along the vascular system itself. And carbon dioxide plays a central role in supplying those protons. When CO2 dissolves into water, it transforms. So CO2 plus water becomes hydrogen and bicarbonate. This reaction is happening continuously, every second, inside the blood, along the vessel wall, throughout microcirculation. And while it's usually described as buffering, it may be doing something more profound, continuously supplying protons needed to sustain vascular separation. Once structured water forms along the glycocalyx, those protons are pushed away from the vessel wall. The wall becomes increasingly negative. The flowing blood beyond it becomes relatively positive. A true electrical gradient emerges, not metaphorically, physically, electrically. And just like a battery, the energy exists in the separation itself. Once those gradients exist, circulation begins behaving differently, not just mechanically, electrically. The glycocalyx creates a charged interface, while the surrounding blood carries a different electrical composition. Together they establish subtle voltage gradients throughout the capillary network. Not isolated events, but a distributed electrical structure, extending through the vasculature itself. The heart remains essential. Pressure still matters, but circulation may depend on more than just mechanical force alone, especially within the capillaries where electrochemical organization becomes increasingly more important. Researcher Stephanie Seneff has compared this arrangement to a capacitor, a system capable of strong separated charge across a structured interface. Viewed this way, the vascular system begins resembling a distributed energy system with stable, continuous, body-wide electrical differentials, extending from the arterial side through the capillary bed and into venous return. Once charge separation exists, movement itself starts generating electricity. When fluid flows across a charged surface, an electrical voltage naturally emerges. This is known as streaming potential. And inside the capillary network, it may be happening continuously. Blood moving through narrow, polarized conditions, creating tiny differences in charge distribution. A voltage builds along the vessel. The capillary is no longer a passive tube. It becomes an active electrical generator. This creates a self-reinforcing loop. Charge separation establishes the gradient. Flow generates streaming potential. That electrical activity influences vascular tone and local flow, which strengthens the gradients that started the process. Each capillary contributing to the larger electrical behavior of the entire vascular network. This may also explain why coherent breathing has such profound physiological effects. Slow diaphragmatic breathing creates smoother circulation. Coherent flow improves conditions for stable streaming potentials. The electrical system becomes more synchronized, more continuous, more efficient. And CO2 maintains this coherence throughout. When it fails, capillary flow fragments, streaming potential weakens, and the body shifts back toward more mechanical compensation. If the vascular system depends on integrated structure, charge, and coherent flow, then disease may begin long before arteries become blocked or blood pressure rises. It may begin with the gradual loss of vascular organization itself. When the glycocalyx degrades, when proton gradients destabilize, when capillary flow fragments, the system shifts from efficiency towards compensation. The heart works harder, vascular resistance increases, yet tissues receive less efficient energy delivery. More energy spent, less order produced. And the consequences may be wide-ranging. Hypertension, chronic fatigue, neurodegenerative conditions, different diagnoses, but potentially connected by the same pattern. Breakdown of structure, breakdown of charge, breakdown of coherent flow. So this is where CO2 becomes therapeutically important. Increasing CO2 appears to move the body back toward coherence, not by forcing circulation mechanically, but by restoring the conditions that allow circulation to organize itself again. So capillary beds reopen, flow smooths out, red blood cells regain flexibility, streaming potential strengthen, energy delivery becomes more efficient. So this may explain why interventions that raise tissue CO2, such as slow diaphragmatic breathing, elevated CO2 exposure, or even transdermal CO2 therapies, can produce effects that seem disproportionately powerful. They may not be simply altering gas exchange. They may be restoring coherence to the vascular bed area itself, not because force was added, but because order was restored. The vessel wall is not passive. Water is not inert. Blood is not electrically neutral. And carbon dioxide is not merely a waste gas. The glycocalyx structures the boundary. Water organizes along it. Protons separate across that structure. Electrical gradients emerge. Movement generates streaming potentials. These create a system that behaves less like simple hydraulics and more like a living electrochemical network, a vascular battery. and distributed throughout the entire microcirculation. So continuously sustained everywhere blood meets structure. And throughout all of it, carbon dioxide acts as a quiet regulator of coherence, preserving the conditions that allow circulation to organize itself naturally, breath by breath. And this brings us back to something incredibly simple. Every breath alters carbon dioxide levels. Every breath influences vascular tone, proton gradients, and the electrical terrain of the body itself. So breathing is not merely an exchange of gases. It is the ongoing act of charging the system that keeps you alive.